should do. So 2 more presentations. They will have a clear beginning and end because they're done, well, both presented by Adam. Another catch is Adam is here today and Thursday. I don't know why he's leaving, but ask him. So really talk with him today. He's available electronically Tuesday and Wednesday, and that will be channeled via the group leaders. Well, hopefully your colleague from the Environment Agency in Cambridge will potentially come tomorrow, but it's still...
Yeah, you really want to come, but he's steps back. Yeah.
It would be really good, David Cotterell, but we'll see how that works out. So, Adam, there's only one change. You're making decisions with probabilistic. Go ahead, Adam.
Okay, cool. Sounds still alright for everyone? Yeah, okay. Okay, so I hope you're all caffeined up after lunch. You've got 2 presentations to sit through now, so here we go. This chap, anyone recognise him? He's my boss. This is James Bevan, Chief Executive of the Environment Agency. And he started a few years back, and pretty much the first thing that happened on it after, I don't know, about a week or so in the job was big floods up in Cumbria. And it's what's interesting is how that's actually shaped his leadership of the Environment Agency while he's been here. If it had been a drought in his first few months of being at the helm, things might have been a bit different, or a pollution incident, but it was a big flood incident. And so he's been really hot on flood incidents. And one of the ideas that he's been really promoting is this think big, act early. So every time we get a sniff of anything possibly happening with a flood event, everyone's manning up in the incident rooms. And that's only possible because in recent years, we've moved to this idea of probabilistic forecasting. I'm sure some of you are aware of. So rather than the past, we used to say, oh, it's going to rain tomorrow. Nowadays, we say, well, actually, there's a few different things that could happen. So here's some examples of what that might look like. And you might assign different probabilities to those, which has been really helpful. So instead of saying it will rain tomorrow now, we might say there's a 30% chance of rain tomorrow. And the good thing about that is it gives us longer lead times, and it allows the forecasters to be more honest about the uncertainties in their forecasts. Problem is, if you're at the Thames Barrier down in London, and we say there's a 30% chance it's going to flood, you can't close the barrier 30%. You have to decide to either close it or not close it. And there's costs associated with every action. So if you close it, you might find that the boats can't get through, even if there's no flood. And here's an example of how you might try and characterise that. So if we say, in the forecast there's 2 options, big flood or no flood, 30% chance of big flood, 70% chance of no flood. And we've got to decide whether we evacuate or not evacuate, as an example. Now this matrix here, I've shown the potential impacts, and for the sake of simplicity, I've done it on a 1 to 10 score. You could put anything in there. You could put pounds, you could put lives lost, you could put roads closed or whatever. But for the sake of simplicity, we're just in a 1 to 10 for impact. So what the story we're telling here is, if there's no flood and you don't evacuate, there's no real impacts. If there's a flood and we don't evacuate, all hell breaks loose. Number 10 there. But if we were to evacuate people before the flood comes, we can bring that down to a 6. But if we evacuate and no flood comes, well, people might get caught up in the mess and everything that happens. People sometimes die in evacuations, even without an incident happening. So that might be a 4 out of 10. So the question now is, do you evacuate or not? A 30% chance. Is that strong enough? I don't know. But I'm sure there's some brains here that could give me an answer. This challenge is, I've got 4 different aspects to it. This is the first one, and this is the simplest element. And to be honest, that's not a very realistic type of decision you'd make in an instant. It's a bit too simple. You're more likely to have something where there's perhaps 3 different forecasts. And again, you then need to look across these range of different ensembles that you might get from your forecast, and so which of those are going to influence your decision. So that's the second one. And a third one would be if you've got multiple forecasts and multiple decisions to make. So do we evacuate or not evacuate? Or do we bring in temporary defences to try and shore things up? And for the temporary defences, it might be that if you get the big flood, they don't do anything anyway. So you might as well have just not evacuated. So some tough choices. What often happens in a flood event is you get these branching decisions as well. So you might decide, okay, we've got forecast and it says there's potentially a catastrophic flood in London. Maybe we just get on with evacuating. Or maybe it's only a 10% chance that they said there's going to be a catastrophic flood. Why don't we wait 12 hours? That's when the next forecast comes out. Now, when the next forecast comes out, perhaps it says it's an 80% chance. Great, well, we'll get on and evacuate. Maybe it's still 10%. Well, maybe we don't need to evacuate then. But the trick with this is, so you could easily, with this branching process, break that down into a number of steps like this, couldn't you? But the problem is that at this point here, where you make your decision to wait, you don't know if the probability is going to change at the next forecast. You might say 50-50 at this point, and you might go to the next forecast and might still say 50-50. So you're taking a gamble. I don't know how you'd quantify that. So those are the 4 examples. So just to recap, we've got a simple binary one. You might have an example where you've got multiple forecasts, and then the example where you've got multiple forecasts and multiple decisions, and finally where you've got this branching structure. Now, my challenge for you is there's 2 bits to it. One is I'd like you to have a go at telling me how I should act for a routine decision. So this is an example of something like issuing a flood warning. So this is the forecast for a deterministic forecast. The red line, when it goes with the red line, is when you decide to issue a flood warning. So these type of decisions are made by people who are trained in the job. They've got tools and systems they use every day. The tools and systems are calibrated around that particular decision they're going to make. So if you were to develop a tool, certainly taking not just a deterministic forecast like this, but a probabilistic or set of probabilistic forecasts, that tool could be quite complex. I don't mind if it's got partial differential equations or whatever inside it, as long as the user can input standard inputs to it and get a standard answer out, that would work for them. So that's the first bit. The more tricky thing, I think, is something like this. Now this is I don't know if it was this bridge exactly. This is a real example. This was in a flood event they had where the water was all backing up because it was restricted at a pinch point in the river, which was around this bridge, and they were worried the river was going to flood the houses further back. So they had one of the incident command rooms. Someone came up with this. They were doing some blue skies thinking, I think, and someone said, "Well, why don't we blow up the bridge? Get some dynamite." Now, there's a real example. I think in the end they decided not to, which I think was probably the right decision. But that kind of example is something you probably couldn't have a model ready-made for to tell you the answer, yes or no. So my next question is can you take something that if you're the kind of person who sits in Gold Command during a flood incident, can you take something that's relatively simple that would help you make a more informed choice, if that kind of question came up for you, but you can calibrate or reshape around a problem you don't know what it is yet. I don't know what the answer to that looks like, but I can show you one example that I thought might work. You might give someone a table like this. So they could look up, and they could probably have a stab. Is it 10, 20, 30, 40% chance of the flood happening or the reservoir failing or whatever the thing is? And I want to make a decision, and the top column headings are how likely I am to regret making that decision. So in the I don't know what the measures you might put across there, but for example, it could be with the evacuation, what happens if you get it wrong? What happens if you make the decision or don't make the decision and the other thing happens that you thought wasn't going to happen? So in this case, is in the top right corner, I can't quite point that high. Can you see that? There we go. So if there's a chance, if the impact of getting it wrong is very high, to 10, and there's only a 10% chance that the flood's going to happen, I say that's a no, probably don't do it. If the impact of making the wrong choice is a 1, it's pretty low, and there's a 90% chance the flood's going to happen, I think get on and do it. I sort of missed off 0% and 100% from this because it's certain then, isn't it? But how might you look at that? So if it was helping you understand what that score across the top might be, I don't know what it is. But I think in this example, this is the simple binary one we showed earlier, I think we don't really care about this one. Because if we choose not to do anything and nothing happens, well, that's fine. And I think we probably don't care too much about the number in this box up here, top left. Because if something happens and we took an action to mitigate it, and then we did the right thing as well, I think the numbers we probably care about are the top right and bottom left. And to be honest, the top right one is probably always worse than the bottom left one. So maybe it's just the top right one. Maybe that's the figure you look up on this table. So that's an idea. Does that make sense to people? There's a lot of furrowed brows as I look around it. But you might have a different idea. It might be there's a simple flowchart you can work through. It might be that I don't know, something else you could use. But again, what I'm interested to know is, can you give me then? So for both those examples, the routine decisions, which is like the flood warning one, where you can use complex tools, or the reactive decisions, like the blowing up the bridge. Can you give me a tool that will work for all 4 of the examples I gave? So the simple binary, multiple forecasts, multiple decisions, and branching decisions. Okay, so just to finish off, the question is why should you be interested in this? I think the thing that's going to be really useful. I think if you're the kind of person who likes taking some complicated maths and boiling it down to something simple that people can use, then I think you'd really enjoy this, because I think this could be something that people use and just carry in the back pocket to a gold command room. So if that's you, have a look at this problem. Any questions?
Coming. Where was it?
Oh, well, okay.
Go.
Hi, I'm Armin from Aalto University. Very interesting challenge, and you have been mentioning the branching decision.
Yeah.
Is there kind of, from system dynamics, a kind of loop decision? So through monitoring, you can revise, or you may be able to revise a decision. Is there something like that? Because at the end, you can measure the water level on the rivers at different positions, and then can you revise your decision in a kind of loop?
I'm just trying to think whether I like the idea of hanging relief. I'm just trying to think how that would look in practice, because I think most of the time you're moving closer and closer to the flood event, aren't you, or the thing happening.
Right.
I can't see a place where you go back in time to the beginning of the decision-making process.
Well, the water is coming from let's say from one region, specific region, and you can monitor the water level there, and you might have a forecast of what's going to arrive afterwards.
So how would that change? So I've got 2 points. So say this is day 1, this is day 2, and this is day 3. How am I going? That's what I guess I'm getting at. How do I go back in time to
Okay,
an earlier point in the decision-making tree?
I see. Okay, I'll think about that. Right, thanks.
So I have a question. The time you need to evacuate is also, of course, a consideration, because at some point you run out of time.
Yeah. You could, if you had here a wait for next forecast as an option here. There might be it might only be don't evacuate here because it's, or not evacuate might be the only option as the next day. Yeah, because you've run out of time.
You had some factor regret. How?
Yeah, this was something like I called it regret. I don't know what, which is on a 1 to 10 scale. I don't know what the measure of regret is, but I think it's something related to this. So it's something like how much I regret making the wrong decision if I now want
Cost or return.
however you're deciding to measure this. So if I'm measuring it on a 1 to 10 scale, but it could be pounds, it could be lives lost, it could be.
Where?
Sorry, Michael Green again. So I have several questions, so I'll try to do them one at a time. The first is whether you tend to look at your decisions as sort of portfolio decisions, so sort of multiple options, or whether you prefer to look at sort of one asset at a time. So it's just an understanding of what sort of tool is more useful.
Yeah.
The second is sort of what level of expertise we should assume on part of the decision maker. So whether they're familiar with things like Bayesian statistics, or whether we're going to have to sort of take a leap.
Yeah.
And then also on this sort of decision tree thing, it's whether you're familiar with things like real options analysis, where you have to sort of calculate the extra costs of having some sort of adaptation in place. So it's just some sort of assumptions. And then I guess the last one to sort of round it up is you want sort of a tool that's fit for purpose. So just a bit of an understanding, is that something like in Excel, in R, in Python, or is it having a suite of tools that, depending on how complex, then we can make something more advanced?
It needs to be an app on your phone, right?
Yeah. Just type it into Google. So the first question was, do we consider things as a system or as individual assets? I think we generally will consider things as a system. When I was thinking about this problem, I couldn't see a difference though between, so going back to this branching one, I couldn't see a difference between, and tell me if I'm wrong with this, having things as a, if nothing changes from decision point to decision point, so if you're saying, well, do we issue the, I'm trying to think of an example now, but okay, one option might be that we store things in the headwaters of the catchment, and then we let it trickle down slowly, or you might say, do we store things in the headwaters of the catchment, wait until the first flood goes down, then let it through in a flush, so we're ready for the next front. I'm trying to think of the things you might do. Do we stack extra stuff on the defences? But so although you might look at your whole thing as a system, and you might have a set of branches there, if nothing's changing from branch to branch, you could break that down into a single set of options, couldn't you? So there's no reason that couldn't be any difference to this. Does that make sense? So you just might have more options. So one of them might have, prepare or put extra sandbags on the defences, then evacuate. The other option might be don't put extra sandbags on the defences and then evacuate. But if nothing's changing between those decision points, you can put them all on one matrix like this, because they'll all have the same probability of flooding. Does that answer your question? Yeah, if there's something I've missed, keen to talk about it with you.
So probably in one other question and then one question on the probabilities that you've got there. So the first one is, if we are going to demonstrate this tool, what sort of data would you prefer us to use? Something like future flows data set, or like the 10,000 ensemble from UK CPO9? Like, what is more likely to be used in the EA? And then just on the probabilities, now they could be one of two things. They could be like classical statistics, frequentis, like the probability of flipping a coin 100 times, or they could be subjective Bayesian, which is sort of what we're moving towards, and just an understanding of whether you're happy with those sorts of subjective probabilities and whether decision makers could, in theory, create their own based on looking at something like that.
Yeah, I'm expecting they will make their own, actually, because I think there'll be, for the simple sort of the bridge thing, what's the probability the things are going to flood? That's not a model that's going to have to tell us that. We're just going to ask them around the room and say, what do you think, guys? I think it's about 70% chance. So I think there'll be, I don't think it has to be classical. I think we have to accept there'll be a lot of judgment and things going on. There were some other questions you asked as well.
Oh, data.
What sort of data? Yeah. So I think most likely people will be using things like the MOG reps. Do you know that Met Office data?
So what are those for
Met Office. Oh, cracky! Anyone else know something rainfall ensemble prediction?
Okay.
Yeah. So 24 different ensembles that make up the. There's a link to it actually in my in the note in the Word document I sent to you. I think that's more likely than the climate change stuff, because that tends to be that's about strategic flood risk management, isn't it? This is something people use in the instant, in real time.
There's a question here. You can ask.
Maxim Ziskin from Nottingham. This looks like linear optimization or two-person game problem. Have you tried this?
I don't know that, I'm afraid. But yeah.
Is there another question? If not, then
Maybe just one comment.
oh, look at it.
Maybe I think that this problem can be framed in the fuzzy logic kind of the things, because these are the approaches which are used for making the informed decision rather than using the Boolean algebra approach.
Yeah,
It's just a kind of a comment.
yeah, sounds good.
Sounds good. Well, I think it sounds good that you now transfer to your last challenge.
Okay.
Go ahead.
Okay. So this last challenge is actually one I presented to you before, and I think we're going to. Our thinking's come on a little bit since last time I spoke to you, so I'm quite excited about it. In summary, there is 1 in 6 properties in the UK is at flood risk, and we want to model and understand that flood risk. And one of the most important inputs to our models is rainfall. Now, typically, the way we'll do our modelling is we'll have a design event, which will look something like this. So we have a summer or a winter profile. You'll pick the one that's most appropriate to your catchment. Typically, it's sort of summer profile if you're doing surface water flooding, and winter profile for big fluvial catchments. And you'll fit that to your return period of flood event. So you'll have a volume of rainfall, and you'll fit that curve to it. And then you'll kind of play with the parameters of it to try and identify the shape that gives you the most damages or properties at risk or whatever is important for your assessment. And then, once you've got this hydrograph, you then assume it falls everywhere uniformly across your catchment at the same time. Now, if you speak to the people in Canvey Island, where the rainfall falls uniformly across the catchment, they'd probably say, no, it doesn't. This is July 2014, and you can see almost here, pretty much no rainfall, and right about 80 millimetres per hour at the peak, so it's a lot of rain. So does that matter? Well, yeah, it does. If your rain falls on the car park here, that's going to be a lot worse than if it falls on an empty field. So there are ways of modelling rainfall in a better way, though. 2 examples are to use Monte Carlo analysis, where you take lots of samples of different rainfall patterns that might fall across your catchment and model those to see how they go. Another option is continuous simulation, where you might take, say, 1,000 years worth of rainfall and then run that through your model and see where it accumulates and where the worst bits are. The problem with both of these, though, is that they take a lot of model runs. And who has money to spend on modelling? Not many people. So what people will choose to do is to just stick with the old approach. So what I'm looking for, I want a way to get the benefits of doing these more advanced techniques, but I don't want to pay for it.
You just had a free lunch.
So that's my challenge to you, is there a better way of doing this? And I think from when we came last time, we had the inklings of an idea that you could use, based on the Monte Carlo approach, but using something called importance sampling. So rather than just brute force randomly taking your samples for the Monte Carlo analysis, that you could explore the probability space a bit more intelligently. So, and I'm led to believe that can reduce the number of samples you need by sometimes 2 orders of magnitude, so which sounds really exciting. So that's the thing that we're hoping you can look at this week. I'm really looking forward to this bit, which is Onno's Metropolis, and the reason we're bringing this down, they're coming tomorrow, is Onno?
Yeah, but they're coming tomorrow evening, but it will be shown on Wednesday.
Okay, fine. So the reason we brought this down is so that you don't have to become a flood modeller in order to try out this approach. So you can focus on doing the statistics, the Monte Carlo analysis, and once you've done that, rather than going and running a ISIS model or whatever, you can put your model into Metropolis and let it run, and we'll see if it improves your run times over. I don't imagine we'd have time to do thousands of Metropolis runs, would we?
Well, the Metropolis day is 10 seconds, so yes, you can.
Oh, really?
It's
Okay.
all scaled,
Okay.
right?
Yeah, yeah.
So it's on purpose.
So we can compare that.
So for the people who have 2D models, and I think there are a few, you could use your 2D model if you think it runs fast enough on your GPU, but the point of mentioning this was that it's very quick. because you tried to sell us some ISIS, but then the license was 20,000. That's not going to work here.
No.
But the basic idea is to come up with strategies and test them for very simple cases.
So, and those cases we'd like to have a look at. I've got 3 examples I thought would be worth testing out. So the first example I'd like to test out is somewhere, this is actually Cambridge, and this is surface water flooding. You can see that almost everywhere is susceptible to surface water flooding. So probably in this example, you might be okay to use a uniform rainfall. So the first thing to check, I think, is that you haven't broken, whatever your Monte Carlo analysis is, it doesn't break the same answer you would have got by using uniform rainfall. You can still get something similar. In fact, this is the flood map for surface water barrier, so it would be, and you'll be aware of it. The second example is to test somewhere where there's Canvey Island, that's what I told you about before, somewhere in the catchment that's particularly sensitive to rainfall. So by assuming that your rainfall is uniform, rather than concentrating a point, you're underestimating the risk to Canvey Island. Whereas if you could have modelled it as being what happens if it's concentrating at one point, it might give you a better idea of what the risk is like. Now, the reason Canvey Island is particularly sensitive to rainfall is it's basically a bowl. So they had to manually pump water out of there 24 hours a day. So that's the second example where there's a sensitive point in your catchment that by assuming it's uniform everywhere, you're not picking up what happens when it's concentrated over that point. And the third one, actually this was on the JPA project, I think, right? Was the Medway model. So what happens with this model is you tend to get fronts of rain coming from the west. They start at the top of the catchment and dump a load of rain there, and then the rainfall front carries on down. And as the rainfall front is carrying on down here, the rain it dropped earlier, higher up the catchment, is passing on down in the rivers as well. And by the time the rain falls here, I feel like a weather presenter, by the time the rain falls here, the rain in the rivers are caught up. So it's much worse than if you assume uniform rainfall at the same time across the catchment. I know, it's shocking, isn't it? So those are the three cases I'll give you. We could probably try and find some data for you, but I think it's giving you use of Metropolis. It's better to try and set up something that represents that problem and demonstrate you can solve it.
But for this one, you had the article which was very clear. Do you have something for the other ones, just to get the essence of what for Canvey Island and for Cambridge?
Well, for Canvey Island, I think you should put a deep bowl somewhere on your model. You could probably just get one from the canteen there. And for this one, we're saying actually everything's pretty uniform. So, okay, so just to wrap up, why should you be interested in tackling this one? I think this will be a really fun problem to have a go at, because you get to have a go at the physical model, the Metropolis model. It's one of those times when you get to physically see the maths, which is quite exciting. And we've also been working with the Urban Drainage Group, Simon's Urban Drainage Group, and they would be keen, if we get something that works with this, to have an addition to their rainfall modelling guide, where we can add a innovative practices section. So if it's something that works really well, they're willing to work with us to put this into industry guidance, which would be quite exciting.
But you didn't put it forward it in a conference yet, did that?
Forward it in the conference?
You didn't submit an abstract to a conference.
No, not for this one. No, not for this one.
So
Cool.
that's it. What?
Yes, but for me, yeah. Thank you.
Thank you. Questions? There you go, Jacques.
So I don't understand the contrast that you're drawing between uniform rain and then Monte Carlo. I mean, you can do Monte Carlo with uniform rain. I mean, how does the Monte Carlo simulation bring in the spatial variability?
It doesn't. Oh, sorry. How does Monte Carlo bring in the spatial variability?
Yes.
I presume for each of your samples for the Monte Carlo analysis, you could have a spatially different rainfall. Couldn't
But
you?
you need to have some information about the spatial temporal structure of the rainfall, right? So you need to know. Whether there are correlations between rainfalling here and rainfalling there.
Yes, you would need to do that.
You can't treat each point as being independent.
No.
But I mean, I guess the weather forecasts do give you the full spatial structure of the rain.
Okay.
Well, certain resolution.
But so I mean, from last time I understood that yeah, you had 5 by 5 kilometer grids for your rainfall. Was it?
No. So 5 by 5 kilometre grids were the tiles for the map surface water. I think the forecasts are, more 1 kilometre grids.
So you put in 1 kilometer by 1 kilometer rainfall information in your flood model. Is that right?
You can do, yeah.
If you had any data, you could infer that distribution that you sample from that data. That would be pretty cool.
Do you in the Medway case you have apparently you put now in a uniform distribution, but you really want which is some average of the detailed one, but what you really want is spatial and temporal, because the rain transport to the city as well,
yes.
And then you get the flood peak as well as the instant rain colliding, and then the old rain which is collected in the flood peak and goes to the river. So that's the spatial temporal.
Yeah, that's right. So with our uniform one, okay, that's uniform. That's straightforward. This with the Canvey Island one, that's we're looking for to show a spatial distribution, and with the Medway, it's a spatial and temporal.
Can I? So I mean, your design events, right?
Yeah.
If I understand correctly, you have a few parameters like for the maximum amplitude and then the width.
Yeah.
These are your random parameters. If you want to do something spatial temporal, then you need more parameters to describe, the correlation lengths. You can imagine having a database of design events which are spatial and temporal at the same time. Right?
Yes.
Do you have such a database? I mean, is there a way of cooking it up?
Can I just come in on that? Because
I'll come to rescue you.
I was going to say the JBA Trust done quite a lot of work on that, and Rob Lamb's work on spatial joint probability event set modelling, and have analysed long time series of TBR, tipping bucket rain gauges, and looked for the sort of fitted the Hefferman and Thorne type approach to joint extremes, so they generate spatially realistic probability fields of rainfall, and then we use those as the set of events. So
that takes your rain gauges as the main point.
Yeah. So it's looking at real data but building the right spatial correlations.
Mm-hmm. So it won't be correlated on every 5 metre grid cell or anything, but it's a bit broader than that. But presumably it interpolates between points.
So you missed my talk because if you're trying, but we did, I don't think I showed it, but we did about 30 events with and without NFM in the Eden catchment, and it was about, I think we interpolated to a sort of 5 kilometre grid over this 2,000 square kilometre. And you did get some pretty, strong gradients and different types of event, and it contrasted to just using a single event from the Met Office for the sort of Desmond Plus event that they modelled.
Yeah.
So it's important to look at lots of different events.
Yeah. Sorry, can I just on that one point there? I think so. The data is available. In terms of what you might do for this week, I don't propose we try and get that data for you this week. I think what we can tell you the sort of format it might be in. But I think if you can invent the data to fit those phenomena that I was describing, so the uniform rainfall.
You see, for Metropolis, the spatial pattern is well known. I mean, I guess, right?
But you could change.
You can invent.
The point is, you can change the model, and you can actually change it.
I guess my question is really: is the difficulty in finding some good statistics for the spatial pattern, or is it or do you have the statistics but you have a sampling issue where it takes too much time to sample?
No, I think we can get that data. So you can either get it from rain gauges. We could, which is a bit more tricky, but get hold of the rainfall radar data, which could be some really interesting patterns to look at. It tends to be less accurate on volumes, but might give you more accuracy in the spatial distribution.
I have a question. It's on the cumulative summation method you propose as an alternative. Could you describe the data source you have for that?
So that's this one.
Yes.
You generally generate synthetic rainfall. So you need some way of understanding the probability to start with, and then you generate a synthetic 1,000-year. So it wouldn't be an actual 1,000-year data source. Yeah.
So I have a question because we discussed this at length. So you're now talking about making a flood forecast with this rainfall distribution. So for the flood risk map, and you have the report in front of me. You use this is the it's called. You send it to me. It's this MDSF2 technical report, and the modeling in there is much easier. Can we use that report because that's very easy? That's an easier way of cooking up a model. So that's really to make the flood risk maps where you just basically fill the box, let the water flow in and let it fill the topography. It's basically just filling boxes. So you don't do any PDE modeling there. It's just filling boxes.
Yeah.
Are we allowed to do that?
You can do, but I don't know how you get the spatial rainfall. I think the way you'd have to do that would be.
Well, you could put the spatial rainfall in, even the spatial temporal. But it's just that then the underlying model which you could use and make up is much simpler.
Well, MDSF2 assumes that the only input you have for the rainfall is that you have, for a range of return periods, different in-channel river levels.
Okay.
So what you'd have to show, you probably wouldn't bother doing any of the MDSF2 modelling. What you'd have to show is that by having a better representation of rainfall, it changes those in-channel river levels, and that would be enough to show that the benefit of your approach.
Or you would have to combine them because the flood peak, with the Medway case, the flood peak coming down you would see in the river level peaks, but at the same time it rains on the location as well in a spatial way combined.
Oh, it does, yeah, but
So
MDSF2 assumes the only water comes in.
I know. But really, strictly speaking, for the Medway case, you have the two approaches coming together because it's the local rainfall as well as the flood peak coming in.
Yeah, and technically the MDSF2 model would work. You can input water at any point.
Am I able to share this report amongst the...
Yes, yeah.
Okay, that's what I wanted to know. Is there another question? There might be more questions.
So just for anyone who wasn't shared, so MDSF2 is a model we use to create the National Flood Risk Assessment. And we're about to move to NAFRA 2, so we're sort of moving on from that approach soon, but it is a model that's in use for now, and possibly is the right word, but an important one.
So I think I can make that even more simple. I mean, most of us live in a house, and you might have bought it, you might have rented it, and you look whether or not on the national maps, whether it is an area of high risk, whether high risk, low risk, etc. And those maps, flood risk maps, are made with this technique, at least last time. And it's a fairly straightforward algorithmic routine given the river levels. And it's feasible to actually model this here, at least for a very small, made-up area. But that's what you look at when you intend to buy a house or when you want to live somewhere and you want to know whether or not you are at risk. That probably everybody knows that here, and if not, we can show you. So, are there more questions on the last challenge or any of the other challenges? You better have a question. Okay, you're not, so that's all right, because now comes tea and coffee and decision time. Now, I already know that some people signed up as basically on the top. They put themselves forward, maybe as a little bit as the leaders of the group. So the next, 45 minutes, try to figure out which challenge you want to be in and sign up. You can still be a little bit decisionless today, but hopefully not too much, because by tomorrow morning you really want to start to get going. So James is here the whole time.
Yep.
So that's good. Barry is here all the time except tomorrow, right? Yes. So at least he's back. So you hit your head tomorrow, and then you won't have a live on Wednesday. So that's very good. Adam is here today. So really, we should all tackle Adam today, but he is on call, and potentially we'll see whether his colleague is here tomorrow, and you're back on Thursday, but you're on call, and we'll take care of that. That ends the presentation of the challenges, and now it's going to be mayhem for 3/4 of an hour. You have to start making up your minds if you haven't done so already. So please join me in thanking all the challenge colleagues. Tea, coffee, and a lot of running around.